Good afternoon everyone. Today we are going to study about singular value decomposition. So singular value decomposition is one of the matrix decomposition methods. Here in this singular value decomposition method, we can write a matrix A as a product of U, sigma and V transpose, where U and V are orthogonal matrices and sigma is a diagonal matrix. We can write U sigma V transpose as U1, sigma 1 U1 V1 transpose, sigma 2 U2 V2 transpose up to sigma R UR VR transpose and so on, where a particular value after k greater than R, all sigma k's are 0 for value k greater than R, where sigma 1 U1 V1 transpose is the major component and all other components are the correction to the term. If we calculate A V, then it is going to be U sigma V transpose and V. As V is the orthogonal matrix, it will V transpose V will going to be identity. Then A V is can be written as sigma U. We can write it as A V1 equal to sigma 1 U1, A VR equal to sigma R VR and A Vn equal to 0. Here the sigmas are related by sigma 1 greater than equal to sigma 2 greater than equal to sigma 3 greater than equal to sigma R greater than equal to 0 and so on. Here as U and V are orthogonal matrices, we can write them as V transpose equal to V inverse and U transpose equal to U inverse. If we calculate A V, we get U sigma as V transpose and V is identity. Then A V can be written as V1, V2, VR up to Vn, and U can be written as U1, UR, Un, and the matrix sigma can be written as sigma 1, sigma 2 up to sigma R and all other components are 0. We can write it as A V1 up to VR equal to U1 up to UR and sigma 1, sigma 2 up to sigma R and all other components are 0. Now these are the salient features of, these are the restrictions on A, U and sigma, like how A, U, sigma are related. Now how the procedure for obtaining U, V and sigma. If we have given a matrix A, then we have to calculate the matrices U, sigma and V for the singular value decomposition. Then if A is given as U sigma and V transpose, if we calculate A and A transpose, it is given by U sigma V transpose and U sigma V transpose, the whole transpose. Then it is written as U sigma V transpose, and when we will calculate it, it will be V transpose of transpose, which is V, and then sigma transpose, then U transpose. As U V and V is the orthogonal matrix, then V transpose and V will be going to be identity. Then we will get U sigma, sigma transpose and U transpose. Now U sigma and sigma transpose is going to be sigma square. As sigma is a diagonal matrix, we can write sigma sigma transpose as sigma 1 square, sigma 2 square up to sigma R square along the diagonal, and all other components are 0 and U transpose remain as it. Then from this equation we can get A transpose U1. If we will operate it on U1, then we will get if you will operate it on U, then U and U transpose will going to be identity, and we are going to get A transpose U1 is sigma 1 square U1. So this is the guiding equation for finding U. A transpose U1 sigma 1 square U1 is the guiding equation to finding all the values of U. Similarly, to find V, the U contains where U contains the eigenvectors of A transpose. If we calculate the eigenvectors of A transpose, then we will get the eigenvectors of U. Now similarly for getting the values of V, if we calculate A transpose A, then it is going to be U sigma V transpose whole transpose, then U sigma V transpose, then it is going to be V transpose of transpose, which is V, then sigma transpose, then U transpose, then U sigma V transpose. Again U transpose U, as U is orthogonal matrix, then U transpose U is going to be identity. Then we are going to get V sigma transpose sigma and V transpose. So as before, sigma transpose sigma is going to give us a diagonal matrix whose diagonal elements are sigma 1 square, sigma 2 square, and so on, and we are going to get A transpose A V1. If we will operate this operator on V, we are going to get A transpose A on V, then this V transpose V will get identity. So we will finally get A transpose A V1 equal to sigma 1 square V1. Now this is the guiding equation for finding a value of V, where V contains the eigenvector of A transpose A. So if we calculate the eigenvector from this equation, then we can get the eigenvectors of A transpose A. So we will be more clear if we will by considering an example. Let us consider an example where A is a 2 by 2 matrix whose components are 6, 0, 8 and 10. If we calculate A transpose, then this is going to be 36, 48, 48 and 164. Now if we get, we are going to calculate the eigenvalues of A and A transpose. So the formula is determinant of A transpose minus lambda I equal to 0, where lambda is the eigenvalue of the equation, which is equal to sigma I square. Then if we calculate the determinant, that is 36 minus lambda from this equation, 36 minus lambda 48, 48, 164 minus lambda equal to 0. So and by solving this determinant, we will get lambda equal to 180 and 20, which are the eigenvalues of the A and transpose, which are the eigenvalues of A transpose, and which is equal to sigma 1 square and sigma 2 square. Now we have sigma 1 square and sigma 2 square as the eigenvalue, and from this we can calculate the eigenvector, which are B1. So the eigenvector corresponding to eigenvalue 180 is given by B1, which is 1 by root 2 1 1, and the eigenvectors corresponding to the second eigenvalue 20, which is given by 1 by root 2 1 minus 1. So these are the normalized eigenvectors corresponding to the matrix A transpose. Now similarly for finding U, the eigenvalue corresponding to the the eigenvector corresponding to the eigenvalue 180 U1 is given by 1 by root 10 1 3, and the eigenvector corresponding to the eigenvalue 20 is given by 1 by root 10 3 minus 1. So these are the normalized eigenvectors. Now we have sigmas, u's and v's. So now we can write A in a matrix in singular value decomposition method as U sigma V transpose. A can be written as U sigma V transpose, which can be written as U1 sigma 1 U1 V1 transpose as sigma 2 U2 V2 transpose. Now we have the values of sigma, U and V. So we can by calculating it, we can write it as 3 3 9 9. These are the components of first component of the first component of the decomposition, and 3 minus 1 and 1 the second component of the singular value decomposition. So this is all about singular value decomposition, and thank you.